All right, now that you've familiarized yourself a little bit with what you need to know in order to be successful at this course, let's actually start talking about what you are going to learn in this course. The main topic is obviously SQL versus NoSQL. So one thing that you've probably seen from the course outline of this course is that this course focuses on Postgres, which is a relational database. And it's a database in which you can model any data for any application. Most of the course is actually going to be concentrated on learning about Postgres as a database. However, the last section of the course, the last lesson, is going to cover a topic that we often refer to as NoSQL or NoSQL. And one of the things that we're going to be seeing as we go through all these lessons is that contrary to what you might have heard, or contrary to what your intuition might tell you, there is actually no clear winner between the two. It's not so much about SQL versus NoSQL as in trying to find the perfect solution, but we're going to figure out throughout the course that different systems can actually be used for different needs. And often, if you're building an application that is complex enough, you might actually need to use both systems together. In the next video, we're going to talk a little bit more about the trade-offs between these two kinds of systems. In the last video, we mentioned how there was actually no clear winner between choosing an SQL system versus a NoSQL system. Since there is no clear winner, it's going to be really important to understand the trade-offs between both systems. You might be exposed to SQL versus NoSQL in two kinds of different situations. In both of those, it's going to be important to know why each system is useful, what are its strengths, and what are its weaknesses. The first type of situation where you might be exposed to this is as a data analyst. And as a data analyst, you often don't get the choice of database systems. The data is going to come from whatever system the developers have chosen, and the more systems you know, the better you're going to be prepared to get the data that you need out of those systems. As a developer, though, it's even more important because as part of a development team, you might actually be implicated in making those tech decisions of what system to choose in order to build the application that your team is building. Not only that, but in addition to making a choice between one system or another, you might actually be compelled to use more than one system, and knowing when to use which is really important. The only way that you're going to be able to do that successfully is if you understand all the trade-offs between those systems and the implication of choosing one for your particular use case. In the next video, we're going to take a look at a little bit of history regarding these kinds of systems and how they evolved to what they are today. All right, now for a little bit of history. Let's take ourselves back a little bit to 1998, which is actually the first time that the word NoSQL was coined. At that time, it was used to designate a relational database that did not use SQL as the language to query it. However, even though that was the first usage of the word NoSQL, it turns out that this is not the common usage today. If we fast forward to 2009, NoSQL has actually been coined as a term to describe databases that are non-relational, meaning that they don't use the relational model, which we are going to learn about in this course. And whereas SQL databases actually are specific to one kind of data modeling, the world of NoSQL is actually much wilder than that and comprises a wide variety not only of databases, but of kinds of databases. So the word has evolved to actually talk about all sorts of databases, going from key value stores to graph databases to document stores and more. And lesson 6 of this course is actually going to be dedicated to talk about these databases and even diving in depth into some of them. One other thing that's important to know historically is that these NoSQL or non-relational types of databases have historically evolved with the usage of the internet. Whether you know it or not, every time you go on a website or do an activity on a website, you're actually generating tons of data. This data is being stored on servers for later analysis. And it turns out that relational databases have historically not been meant to store and process these huge amounts of data. which is where these non-relational databases have started to come into play in order to complement relational databases. Now that we know a little bit more about the subject at hand, let's move on to the next video where we're going to look at how this course is organized. So in the previous video, we've looked at a table, and you've sort of had to believe me that there were some things that were weird with that table. Let's bring it up again and talk about what kinds of anomalies denormalized data can cause if you keep it in your database system. These anomalies are usually split into three different categories. The first one is what we refer to as insertion anomalies, and this would happen when you're inserting new data into a table. Again, if we keep to this example, you'll notice that item number 12 here, which is called Happy T-shirt, already happens twice in the data. There is a kind of duplication that's going on here. And one thing that can happen as we're inserting more rows of data for the same product, well, someone could make a mistake in the name of the product. For example, spell happy in a wrong way or something like that. It happens to all of us because there is some human element involved in inserting new data. This is happening because the data is actually duplicated. The second type of anomaly that can happen is called an update anomaly. We actually have an example of that just in this small data set right here. You notice that variant 1 here has at some point in its existence been renamed to white with a code WHT at the end, but that other repetition of that same variant here does not have the code. This is what we call an update anomaly because at some point, again, a human updated this data and did not update it everywhere. If this data was not duplicated, then this would not happen. Finally, the last type of anomaly that can happen is called a deletion anomaly. An example of where we can see this is the sunglasses item, which only has one variant, and there are 5 items of that variant. What if we sell all of them and suddenly there is no more quantity for that variant 1? Do we delete that whole row? If we delete the whole row, then we completely forget about the sunglasses product and it completely disappears. The intuition here is that if you look at this table, we actually don't have just one type of data, but really 2 different types of data. We have items, which are on the left side of my pointer, and we have variants, which are on the right side. Starting in the next video, we're going to start learning about the normal forms of data, and we're going to start to see how to split these things so that we can actually get rid of all the anomalies that we just saw. In the last video, we talked about how having denormalized data can cause some anomalies when you actually start interacting and manipulating that data. In relational theory, which is a subject that we're not going into in depth in this course, there is a structure or a process that is explained where you can take some denormalized data and bring it through various so-called normal forms. In the next few videos, we're going to explore these so-called normal forms. We're going to talk about the rules that drive them, and we're going to look at some examples so that we can evolve denormalized data into better and better and more normalized forms of the same data. Specifically in this video, we're talking about first normal form, which is actually happens to be the most intense because we're taking data in its worst possible form and we're starting to try to make it better. Let's first go through the rules of first normal form, and then we're going to look at an example. The goal number 1 of first normal form is to have the same data type in a column. Goal number 2 is to have a single value in every cell. Goal number 3 is to have no repeating columns. And goal number 4 is to be able to uniquely identify a row. And we're going to look through the example that we had in the previous video at how we can actually start doing this by taking those rules one after the other and applying them to the data set that we have. So this is the table as we saw it in the previous video. One of the first things that we had noticed was this quantity column here, where we have numbers, but we also have text that represent numbers. This breaks the first rule of first normal form, which is that we need to have the same data type in a column. So here we have numbers and we also have text. And even though that text represents numbers, This is not good enough. So we're going to make a change everywhere. We're going to change this 11 to be a number, but we're also going to make some other adjustments about data types. You notice that they're all in bold here. Wherever we did not have a variant code, we actually went ahead and added a variant code so that all the data in the variant columns are actually of the same data type, which is a name followed by a code. Having done that, we've actually finished obeying the first rule of first normal form. Let's move on. The second rule says that we should have a single value in a cell. Well, even though it might not be obvious, we're actually breaking that in one place in this data set. In this variant column, we actually have two things at the same time in the same cell. We have a variant name and we have a variant code. And while this might be perfectly legible to you as a human, computers like data to be a little bit more organized. So we're actually going to fix that. And this is the way that we're going to fix it. We're going to actually have a separate column for the variant code and the variant name. So you notice that we added quite a few columns to this data set now. Each variant now has a column for its code and a column for its name. But this has made it so that we've obeyed the second rule of first normal form, which is to have a single value in a cell. This pattern can actually show itself in another form completely. So let's take a break from this items data set to look at another example where we have single values and we need to break them up. In this table on the left, we have a table of customers with a customer number, a customer name, as well as a column that contains phone numbers. And again, even though this may not be immediately obvious, you can see that in the same column here, called phone numbers, we actually have more than a single value in a cell. Some people have multiple phone numbers, which is perfectly valid. You probably have a home phone number, an office phone number, a cell phone number, or at least some of these. And it turns out that databases don't like that. So when we have multiple values of the same kind in a column, we can actually fix it by spreading out those rows into multiple rows of data. You notice that Alice has one phone number. So in the new data set, Alice still only has one row associated to her. Where Bob had two phone numbers, there are actually now two rows associated with Bob. And where Cindy had three phone numbers, there are now three rows associated with that. So in this example, we've actually obeyed the single value in a cell rule of first normal form by splitting up the data vertically and adding more rows. You may also notice that we've created some duplications in this case, but in further videos, we're going to see how to fix those. So don't worry about that right now. This was a separate example of how having a single value in a cell can happen and how we can fix it. Let's move back to our items example and look at the third rule of first normal form, which is no repeating columns. We identified that problem early on as we were exploring this data set, which is that we have repeating columns in the form of variants. We have variant 1, which comprises a code, a name, and a quantity. And then we have the same thing for variant 2 and variant 3. And we already said that this is not very scalable. If an item has more than 3 variants, we actually have to change our whole database schema just to accommodate that. And this is not actually really easy to do in practice once you start having hundreds of thousands of items in your database. So how do we fix that? Well, we're going to do it very similarly to how we fixed the phone numbers example. We're going to bring this data back down into one column for the variant, and we're going to duplicate rows of data where we have multiple variants. So this will make the table look quite different. And the table will now look like this. Notice that we don't have repeating columns for the variants anymore. We've now split those up into rows of data, where our Happy T-shirt product, which had 4 variants, now actually has 4 rows of data, but only one variant column in each row. Notice that this is also causing the same kind of duplication of data that we saw for the phone numbers, but in further lessons, we're going to see how to fix that. Remember, We're slowly taking steps in order to bring our data into the form that relational databases want us to have it. And in order to do that, there are going to be some awkward middle steps in the process. But trust me, as we go through this data will make a lot more sense. For now, just know that we're trying to blindly obey a rule, which is to have no repeating columns. Now that we've done this, it actually brings us to the last and final rule of first normal form, which is to be able to uniquely identify a single row. And it turns out that for any given data set, there might be multiple ways to do that. The general principle is to look at the data and to identify something that we call a candidate key. A candidate key is actually a set of columns that you can point to that will uniquely identify a row in this data set. So if we look at an example here and we look at the second row of data, and I ask you, which data points could you use to uniquely identify this row of data? Can we just use the item number to uniquely identify this row? Well, clearly we can't, because we can see that this item number appears multiple times in multiple rows of the data. So if I tell you the row with item number 12, well, you can't tell me exactly which one I'm talking about. Even if I use a combination of item number and item name, you still can't tell me which row I'm talking about, because these are also duplicated. However, if we look at item number and variant code, now we can see that those are unique across the dataset. This dataset is actually describing the quantity for an item and its variant. So it kind of makes sense that identifying a row by item number and variant code is a unique way to do that. So in the jargon, we will say that item number and variant code together form what we call a candidate key, which is a set of columns that can uniquely identify a row in this data set. There is another combination that we can use to uniquely identify each row in this data set, which is the item name and the variant name. And we can also mix them up. We could use the item number and the variant name, and so on and so on. The important is that we actually have a bunch of different candidate keys or set of columns that we can use to uniquely identify this data set. At the end of the day, we will have to choose one that we will call the primary key. We're going to talk a lot more about primary keys in further lessons, but for now, let's just know that the primary key is the key that we will choose as the candidate key that will uniquely identify a row in this data set. For this current data that we're looking at, I am going to choose item number and variant code to be the primary key. Why am I doing that? It turns out that in practice, it's better to choose codes than made up human names as the primary keys, because those tend to be more consistent. But as we go through the other normal forms and as we go through designing our own data, you will actually get a much better intuition into what primary keys should be for the data sets that we're going to create together. Well, we've done it. We've gone through the 4 goals of first normal form, and we've ended up with a table that satisfies all those rules. Even though this data might look a little bit awkward, in the next video, we're going to actually start looking at second normal form, which is going to take the same data and actually start making it look a lot nicer and eliminate a lot of the repetitions that we have in there. But before that, you're going to take a few quizzes and exercises to make sure that you've understood this content well. Great. Now that you've mastered first normal form, let's start talking about second normal form, which is going to take us again closer to how relational databases want data to be stored. Thankfully, the goal number 1 of second normal form you already know about. It's bringing your data to first normal form. A table can only be in second normal form if it's already in first normal form. And there's only one more goal in order to achieve second normal form, which is to have no partial dependencies in your table. Now, even though that's just one goal, it brings up a very important question. What is a dependency in the context of data? Well, let's take a look at that. dependencies are actually a topic that is related to primary keys. So let's take a look at this data set and first take a look at what the dependencies are qualitatively, and then we're going to define what a dependency actually is. So in this data set, we've identified that the primary key here is composed of item number and variant code. And so let's take a look at the rest of the columns. All those columns that do not actually compose the primary key, that key with which we can uniquely identify a row in this data set. So the first column is item name. And the question that we have to ask ourselves is, what does item name actually depend on in terms of the primary key? Does item name depend on item number? The answer is yes, it does. Meaning that if you have an item number, you can deduce the item name from it. This is what we call a dependency. Now, does the item name depend on the variant code? Well, not really. If I give you a variant code, you can't tell me anything about the item. Case in point, you can see that this WHT variant code here is used for the happy shirt item, but it's also used for the dress shirt item. This means that the item name does not actually depend on the variant code. So right now, it only depends on the item number. Let's move on to the second column, which is the variant name. Does the variant name depend on the item number, the first part of that primary key? Well, I'm going to tell you that no, it doesn't. The variant name has actually nothing to do with an item number, the same way that the item name has nothing to do with a variant code. If I give you an item number such as item 12, you cannot tell me anything about a specific variant name. Item 12 has 4 different variant names. And just knowing the item number cannot tell you what a variant name is. However, variant name is fully dependent on the variant code. There is a 1-1 relation between them. If I give you a variant code, you can immediately tell me which variant name I'm talking about. There is a direct dependency between the variant name and the variant code. And let's move on to the last column of this data set, which is the quantity. So what about the quantity? Let's talk about that qualitatively. What does the quantity actually describe? Well, if I had to put it in human terms, the quantity describes the numbers of a variant of a certain item. So for the happy shirt, we have 11 yellow happy shirts. We have 5 black happy shirts, and so on and so on. Or another way to put it, if we want to talk about it in terms of the primary key, is that we have 11 of item number 12 for variant YLW, and so on and so on. All this to say that the quantity column actually is the only column in this data set that depends on both parts of the primary key. Another way yet to put it is that you cannot simply talk about the quantity of yellow shirts. Sorry, you cannot only talk about the quantity of happy shirts. You have to actually talk about the quantity of a variant of an item. So to repeat, the item name only depends on one part of the primary key. The variant name only depends on one part of the primary key, but the quantity is actually describing a value that depends on the full primary key. It depends on both item number and variant code. So now that we know what a dependency is, we can actually talk about the subject of second normal form, which is partial dependencies. Well, what is a partial dependency? It's where a column that is not the primary key depends only on one part of the primary key and not on the full primary key. So in this table, both item name and variant name have what we call a partial dependency on the primary key. You can actually notice this in a way when you see that there are duplications here in this data set, right? We don't need to have the item name in this table. Only having the item number is sufficient. we don't need to have the variant name. Only having the variant code is completely sufficient in order to describe this dataset. Eventually, we're going to need to know that item number 12 represents happy shirt, but we don't need to have that information 4 times. So now that we've identified our partial dependencies, well, let's talk about how we go about eliminating them. This is actually going to be much more straightforward than you might think. Eliminating partial dependencies is first done by removing those columns from our initial table that were causing partial dependencies. So we're now left with only the primary key as well as the quantity column, which is the only column that was fully dependent on the whole primary key. So what do we do with the rest of the data, which comprises those variant names and those item names? Well, we give them each their own table. And that's it. We have now achieved second normal form. Actually, I would like you to notice that the 2 new tables that we created only contain 1 column for the primary key, which I've decided to call ID. This is completely arbitrary, and you can call that column however you like. But the important thing to note here is that this primary key of these 2 tables is comprised of a single column, whereas the primary key of the variance table is composed of 2 different columns. We call this a composite primary key. Composite simply means that the primary key contains more than 1 column. And since a partial dependency can only happen when a column depends on a part of the primary key, we can be sure that there are no partial dependencies in the 2 new tables that we created because their primary key is composed of a single and unique column. This means that there is no way that the rest of the data can depend on a part of that primary key because it only contains 1 column. And that's it. Just by virtue of doing that, we have achieved second normal form. So let's recap what we've done here. As a first step, we've brought our tables in first normal form. We just achieved that by taking the table that we had from the final form of first normal form. And the second thing that we did was to eliminate partial dependencies. The recipe that we followed to do that was to first identify those partial dependencies by going column after column and determining its relationship to the primary key. And finally, we've created new tables where needed so that we can move the data that was partially dependent on the primary key to its own table. And that's it. Once we've done all of that, we have achieved second normal form. This is bringing us one step closer to the final form that databases want us to have in order to store our data in an efficient manner. Before we move on to third normal form, which is the last one that we're going to learn about, you're going to go through some quizzes and exercises to make sure that you've understood this material properly. Wow, we've already gone through a lot, but trust me, we're almost done with this. You can already start to see the rewards from the last exercise that we did, where we eliminated a lot of repetitions and are starting to make our data more consistent. This is bringing us to the final part of this data design system, which is called third normal form. And again, it's only comprised of 2 goals. The first goal is going to be to bring data to second normal form, which by now you've become an expert at doing. And the second and only other goal is to eliminate all transitive dependencies. We already know what a dependency is a little bit, but we don't know what a transitive dependency is. So the original definition of a transitive dependency is when a non-key attribute determines another non-key attribute. I think this is best seen by looking at an example, because definitions can often be confusing, and seeing an example will actually make it a lot clearer. To do that, I'm going to bring back our expenses table from the second normal form exercise, and only the expenses table for now, because it actually exhibits one transitive dependency. If you've already had an intuition on that, it's great. Let me walk you through it, and let's actually eliminate that together. So we already know that a dependency is when anything that is not a primary key depends on the primary key itself. The second normal form was dealing with partial dependencies, which is when a column depended only on one part of the primary key. And one thing that we can be sure of is that this expenses table, which contains only a single column as its primary key, cannot have a partial dependency. No column can depend on part of the primary key because the primary key is only composed of one column. So let's take a look at some of those. Specifically the employee ID column. Well, if I had to say this in human terms, I could say that expense ID number 1 belongs to employee ID number 5. So that employee ID is actually dependent on the ID of the expense. What about the employee name? Well, if I had to say it in human words, I would also say that expense ID number 1, instead of saying belongs to employee ID number 1, which is actually not very human, I would actually say expense ID number 1 belongs to Bob. Or even another way to say it would have been that Bob incurred expense ID number 1. So intuitively, it might seem like the employee name column is also dependent on the ID column, just because of the way that I've stated my sentence. But there's something hidden here, which may not be immediately straightforward. This employee name column actually, yes, does depend on the primary key of the expenses table, but it depends on it through the employee ID column. What I mean by that is that if I only have the employee ID column, then I have all the information that I need to qualify this expense. Knowing that employee ID number 5 is Bob is an important information, but it does not need to be part of the expenses tables. The expense table should only describe expenses and should not be describing employees. This is a little bit more visible for these two other expenses. Expenses ID 2 and 3 both belong to employee ID 42. There's nothing wrong with that. An employee can have multiple expenses, but we can see here another form of repetition where the employee name for Travis is repeated twice. In terms of the pitfalls that we talked about, you can clearly see that this is a cause for both insertion and update anomalies. If I insert a new expense for employee ID 42, there's a chance that I might misspell their name. If Travis updates his legal name, then I'm going to have to update this in every row of the expense table, and this is another chance for me to make mistakes. So clearly, even though the employee name seems like it depends on this primary key, it actually depends on it through the employee ID. And this is exactly what is meant by a transitive dependency. It's a dependency on the primary key through another column which is not part of the primary key. This kind of dependency causes duplications in the data, and thankfully it can be fixed. So the way that we're going to fix it is by following a very similar process to second normal form, where firstly, we are going to remove that column from the data set. Notice that the employee name column has been completely removed from this data set, but we haven't removed any information from the data set. We always have each expense associated through an employee by their employee ID. And we've already identified that employees are their own entity. So what we're going to do is we are going to do exactly the same thing that we did for second normal form, which is that we are going to create a new table of employees where each employee will have their own ID and where the name of the employee will only appear once. Notice that we've gotten rid of duplications here, so that if Travis, who has 2 expenses, wants to change his legal name, well, now we only have one place where we need to change it. There's another cool thing about this. By having employees in their own table, we can now actually have employees who do not incur any expenses. This is something very important. By identifying employees as their own entity, they can exist independently of expenses. And this is really the gist of third normal form. Even though there are rules to follow and recipes to follow, the intuition that you should have about this third and final normal form is that every entity in your system is entitled to have its own table so that it can be created, modified, and managed separately from all the other entities in your system. This is the final goal of third normal form, and this is the ideal way in which databases, relational databases at least, want us to store data. So as a quick recap, bringing data into third normal form is done by first bringing the data into second normal form, which means bringing it to first normal form and eliminating all partial dependencies, and finally eliminating all transitive dependencies, which, to remind ourselves, is when a column depends on the primary key but through another column. And the way that we do that is by first qualitatively identifying those transitive dependencies. That means looking at the data and being intimately familiar with that data. And finally, once we've identified those transitive dependencies, which again are non-primary key attributes that are determining another non-key attribute, well, we're going to follow the same recipe as second normal form and create new tables for each entity that we've identified. And this will bring us to third normal form, where we will have no repetitions and where we will have the data in the most efficient way for our relational database to be able to process it. While we are done talking about all the third normal forms, you're now going to be doing some exercises and quizzes to make sure that you understand that material properly. After we do that, we're going to look at some special cases where some of those rules don't always have to be obeyed. So far, we've seen how databases would like us to ideally store data so that they can manage it in an efficient way. We've done that by going through 3 different so-called normal form, where each of them had very specific rules that we had to follow in order to make the data more and more manageable with less and less repetitions and less chance for mistakes. These rules apply most of the time. However, in real life, data is not always perfect. There are some cases where we need to bend the rules a little bit in order to be able to have some convenience about what we're doing. So it turns out that in practice, there are some database schemas that violate third normal form, that do not actually obey all those rules. And sometimes, frankly, it's quite acceptable. You're going to have to use your intuition as you're designing schemas to figure out whether sometimes you might be going a little bit too far. And in order to help you hone in on that intuition, I would like to go through an example with you. A very common example where following third normal form will actually not only be tedious, but will be borderline on ridiculous. So let's jump right in. This is a very standard database table for any kind of shopping cart or e-commerce system. It's composed of customers, where we can see that the primary key is the customer ID, and then we have a few other columns that describe that customer. We have the name of the customer, we have their street address, city, state, zip code, and well, this data looks quite okay, right? Looks quite normalized. There are no real duplications. There's a unique way to identify each row in the data set using their customer ID. Each column contains the same type of data, city, states, and zips. There are no columns that contain multiple values or anything like that. So it seems like this data is quite okay. But if we go back to the rules that we talked about, specifically if we talk about the rules of third normal form, there are some hidden things in there that may not jump to your eye right away. And in actuality, maybe they shouldn't even jump to your eye. But for this specific example, I would like to show them to you. So if we look at the city, and we look at the city of New York, the city of New York is forever and ever always going to be in the state of New York. So we can already see that there is a kind of dependency here, in the sense that if I know that you live in New York City, then I also know that you live in New York State. If I know that you live in San Mateo, then I also know that you live in California. So there seems to be some kind of duplication going on here, which might make you think, oh, well, I need to do better than that. And going back to our pragmatic approach to solving third normal form, where we said that we are going to identify every entity in this data set, well, there are two ways that we could look at this data set. We could see those 4 columns as being one entity that represents an address, someone's street address, or we can actually see them as separate entities. A state is a separate entity. It can have its own ID, and it can have the state abbreviation as another column in the data set. And if we push that even further, well, cities can also be their own entity. And we can associate each city with the ID of the state that it belongs to, so that we don't have these kinds of duplications anymore where New York is in NY state, something that should be determined one single place from this data set. But we can even go one step further. We can do the same thing with zip codes, right? I mean, zip codes belong to a city. I might be simplifying things here and not respecting exactly what USPS does with zip codes, but bear with me here and just see that I'm trying to really push this example to its extreme and try to extract all entities from this and try to associate them together. And if you think I'm done, well, I'm even going to go one step further. You could imagine in a certain system that a zip code actually represents one street. So for example, Main Street could all have the same zip code. So Main Street in New York City in New York State could always be the zip code number 3, which is 19127, for example. So that would be something that's really possible in practice. And so if we go overboard with this and identify each of those parts of an address as its own entity, then we don't actually need to have them all in this table. We could say this table is not in third normal form because there are a lot of transitive dependencies here, and actually move this table to only have a street number and a street ID. And just to prove it to you, let's actually see and prove to ourselves that we can reconstruct the full address from this awkwardly normalized data set. So Alice's address originally was 123 First Street, New York, NY 10101. In the new data set, we only have 123 and the street ID. So we've successfully and awkwardly eliminated all transitive dependencies. Let's see if we can reconstruct the full address. So from street ID number 3, I can go in my streets table and figure out that street ID number 3, okay, I messed up my IDs here, but we'll fix them later. I just want to continue here. That street ID number 3 is Main Street, which has zip code number 3. And we can see that zip code number 3 is 10101, which belongs to city ID number 1. And then we can jump back to the cities table and see that cities ID number 1 is New York, which belongs to state ID number 1. And then we can jump back to the states table and see that state ID number 1 is New York. So just by having the street number and the street ID, we are actually able to reconstruct the full address and fully separate our entities and fully separate our data into obeying third normal form and eliminating all transitive dependencies. Is this practical? Not at all. Imagine trying to reconstruct something like this using the SQL data query language that you already know about, the amount of joins that you're going to have to deal with, and what your query will look like in the end, only in the name of obeying third normal form. In practice, for addresses and other kinds of information that does not change often, it turns out that we do not obey third normal form. And this is one perfectly valid edge case where we store a customer's full address into this as a single table. Not all systems do that, but I'm using this example to show you that sometimes obeying those rules of third normal form and taking them to the extreme can cause situations where you're actually shooting yourself in the foot and doing things that are going against your initial goal of making it easier for you to manage the data. So keep this in mind as you're designing your own data set, that the third normal form is often very valid and very useful in order to avoid repetitions and in order to make your data more manageable, but also that you have to use your judgment in addition to the rules when you're designing your own data sets. I hope you're as excited as I am, because in this video, we're actually going to create our first table inside the Postgres database system. Let's take a look at the syntax to do that. The syntax for creating a table is writing the keywords create table, followed by a table name, followed by a parenthesis, followed by a comma-separated list of columns and their types, followed by a closing parenthesis and a semicolon. A few things that are important to note here is that case does not matter. You can write create table in lowercase, in uppercase, in whatever case you like, but SQL programmers generally prefer to write the keywords of the language using uppercase. Another thing that I'd like you to note is that table and column identifiers in Postgres are double quoted. And while this is optional, I would strongly advise you to always double quote your names. Why? First, because in case they clash with a keyword from the language, it won't be an issue if they're double quoted. But also, by double quoting them, you are making your SQL easier to read for yourself and for other people when it comes time to revisit a command that you've previously written. Let's take a look at some of the data types that we need to create tables. A lot of the further videos in this lesson are dedicated to looking at the wide variety of data types that Postgres provides. But for now, we need at least 2 or 3 just so that we can get started creating our first table. So the 3 data types that we're going to be using in this first demo are the text data type, which allows us to store text values, the integer data type, which allows us to store integer numbers, as well as a special type called serial. We have almost a full video dedicated to the serial data type. But for now, let's just suffice to say that the serial type is a type that we can use specifically for those primary key ID type of columns. So armed with the knowledge of the syntax on how to create a table, as well as a few basic data types, we're now ready to create our first table inside Postgres. Normally, you might be compelled to jump right into your Postgres command line and just start writing your SQL right here. However, my personal preference is to use a text editor in order to be able to type my command in a more relaxed atmosphere where I can more easily edit it if and when I make mistakes, and also have the benefit of syntax highlighting. When I write SQL in my text editor, it automatically gets syntax highlighted, which makes it easier for me to know if I've made a mistake and also easier for me to make sure that I'm writing the correct syntax. So let's go ahead and create our first table. We're going to create a table of students for this demo. So I'm writing create table students. Notice that students is in double quotes, followed by an opening parenthesis. And here I'm going to skip a line and I'm going to indent by 2 spaces. While this is optional and SQL doesn't care about white space, I'm actually doing it so that it's easier to read. So I'm going to create an ID column for my student, and I'm going to give it that serial type that we just saw earlier and that we said was a good type to use for those ID type of columns. We'll learn a lot more about the serial type later. For now, we're just getting into the motion of creating our first table. I'm going to give students a name, which I'm going to make of type text, followed by a comma. And then I'm going to, just so I can use that integer type, I'm going to give the students a fictitious column name of rank, which I'm going to make of type integer. Notice that I don't put any comma because I'm done with my list of columns. So I'm going to just close the parenthesis. Notice again here how my text editor is helping me by highlighting the opening and closing parentheses. And I'm going to put a semicolon. This is the first time that we're writing DDL together. So now let's take this command and I'm going to copy it and I'm going to paste it right into my Postgres command line, which is the command line that gives me access to my database system. So I'm going to paste the command right in and I'm going to press enter. And Postgres is going to tell me create table, which I'm supposed to believe that the table was created successfully. You already know how to check that because you're very familiar with the SQL DQL, which is the data query language. So you already know that you can say select star from students. Notice that I'm double quoting students here, even though it's optional, just to make sure that I know that it's an identifier. And I can see that my table of students was created with an ID, a name, and a rank column. And well, there is no data because I just created that table. Now, how do I know that those column names are actually of the proper type? Well, I'm going to show you two commands that you're pretty much going to use every day that you're using the Postgres command line. The first one of those commands is \dt. If I write that and press enter, Postgres is going to give me a list of all the tables in the database. Now, this is a brand new database and I've only created one table, but I can see here that there is a table called students in my database. The second command, which you're going to use extremely often, is a \d followed by a space and followed by the name of a table, like students, for example. You can think of D as describe if it makes it easier for you to remember it. And this is going to describe to us the students table. So starting from the bottom, we can see that we have a rank column, which is of type integer, just as we intended it to be. We have another name column, which is of type text, just as we intended it to be. And then we have an ID column, which is of type integer, even though we specified that we wanted a serial type. As we'll see in a later video, serial is one of those types that is called a convenience type, where under the hood it's an integer, but it's automatically managed by Postgres using something called a sequence, which means that Postgres will be able to automatically generate ID values for us without us having to manage and remember to do that. For now, the important here is that we've created our first table and we've learned how to verify that that table exists in the system using the \dt command. And we've also learned how to verify that the structure of the table matches what we wanted it by using the \d command followed by the name of that table. After you go through a few quizzes and exercises, we are going to start looking together at the wide variety of data types that Postgres provides to us in order to represent real-world data. Now that we know how to create tables in Postgres and we've started looking at a few basic data types, it's time to dive right in and look at the wide variety of data types that Postgres provides to us. We're going to split those up into different categories, and in this video, I'd just like to show you all the different numeric data types that Postgres makes available to you. And actually, there's a lot more than you might think. Postgres provides to us, in terms of numbers, small int, integer, big int, decimal, numeric, real, double precision, small serial, serial, big serial. Wow, that's a lot of data types. And it might sound like you would have a hard time figuring out which one to choose for which situation. But don't worry. In the next two videos, we are going to go slowly about dissecting all of those data types, figuring out that a lot of them are very equivalent to each other, and at the end of those two videos, you're going to be in a better position to choose which numeric data type is best to represent which real-life situation. In the next video, we're going to start looking at the integer types of data. In this video, we're going to start simplifying all those numeric data types that we just saw by looking at the integer data types. So Postgres provides to us small int, integer, and big int. The good thing though is that even though those are three types to represent integers, they all behave exactly the same way. The only difference between them is the range of numbers that you can store. So depending on which type of number you need to store, well, you can choose either of those three. Now, hand in hand with those three integer types, Postgres provides to us three sequence type of integers, which are called small serial, which kind of links to the small int type, and then serial, which links to that integer type, and big serial, which links to that big integer type. You can already see here that one of the big differences is that those numbers start at 1. There cannot be a 0 or a negative number. And actually, what those numbers are again very simple integers, but Postgres can automatically produce and incrementing sequence of those integers whenever we don't provide a value to it. So in order to understand how this automatic generation works, I've set up an example table for us that is going to make use of these integer types, and we're going to go through it to understand better how they work. So I've already set up a table for us, a table of employees that uses an ID column, which is of that serial type, a name column. I've actually had to put a text type in there, even though we're learning about numbers, just so that the data makes more sense, and a salary column, which I've chosen to make a small int. Small int, if you remember from the slide, is about between minus 32,000 and plus 32,000. So let's go ahead and just copy this and paste it into our Postgres command line. And again, if I go \d and I say employees, we're going to see that the table was created exactly as we intended it, with a small int column, a text column, and that serial column, which was actually an integer that has as its default value something called next val of employee IDs sec. So even though we're only going to start looking at how to manipulate and insert data into tables in the next lesson, I've actually prepared some insert statements for us here so that we can see for ourselves the behavior of this serial type, which I told you was an integer. So here, I've prepared a command for us that we're going to run into Postgres, which is going to insert into the employees table some values. What I'm doing here is I'm telling Postgres that I only want to target the name and salary columns when I'm inserting data. So notice that I'm not touching the ID column here. And after the word values, I'm actually listing two sets of values. I would like to insert a row for the employee Alice with a salary of 25,000 and another row for employee Bob with a salary of 22,000. Notice that again, that I'm not doing anything about the ID column. So let's see what happens if I try to insert this data into the table that I just created. I'm going to copy this command and again paste it right into my Postgres command line. Notice that Postgres replies with insert, and you probably already know that you can just do select star from employees to see what kind of data is available in there. If all you want to do is select star from employees, Postgres has a little shortcut for you that you can use, which is when you just want to explore what kind of data there is in a table. And I'm going to show it to you. You can just write the word table followed by the name of the table. So let's say you would write table employees using that tab completion that I taught you about earlier, and followed by a semicolon. You will see that the data that we asked Postgres to insert was inserted. Alice with a salary of 25,000, Bob with a salary of 22,000. And look at that ID column here, which we have not even targeted when we were inserting those values. Alice has been assigned ID number 1, and Bob has been assigned ID number 2. This was automatically done by Postgres because we did not specify a value for the ID column. Postgres automatically used a sequence of numbers that it created for us, and for every new row that we add to this table, we will never have to specify the ID, and Postgres will automatically generate it for us, making sure that we have an incrementing unique ID for each row in our table. This is exactly what the serial type is for. Now I can prove to you that the serial type is nothing more than an integer. If I go ahead and do select star from employees, where the ID column, which is supposed to be a serial, is equal to 1, which is definitely an integer, if I run this command, Postgres will have absolutely no trouble comparing the serial ID column with the integer 1 and producing to me the right answer, which is the employee Alice with ID number 1. So remember, serial is a great way to generate integers automatically and use them as the unique primary key of tables that need them. Now, let's take a look at one more example that will show us the implications of the data types that we've chosen. I've prepared another insert statement here, which looks very similar to the first one, and is trying to insert a third employee in this table called Carol with a salary of $45,000. So I'm going to copy this statement. I'm going to add a semicolon at the end of it, and I'm going to copy it. And then I'm going to bring it again right into my Postgres database. I'm going to paste it, and then I get a problem. Postgres did not insert this employee into the table. Why? Because small int out of range. So notice that because I made the decision to use the small int type for the salary column, I have limited myself to values of salary between minus 32,000 and plus 32,000 or something. It's actually 32,767 to be precise. But the point is, I have made a decision that is impacting the kind of data that I can insert into my table. In later videos in this course, we are going to see that we can modify the type of a column even after we've created it. But that's not something that you want to do because it's a process that takes time and that is error prone. So I just wanted to show you this example in order to insist on the importance of designing your data types properly. There is a reason why Postgres provides 3 types of integers to us so that we can choose the best one for the best situation. So in this case, for the salary of an employee, if we look back at the integer types that we have, well, we can see that the best type to have chosen would probably have been the integer type, which provides values that go way upwards of 2 billion. In the next video, we're going to look at another type of numbers, which are the decimal numbers. So we're continuing on with our simplification of all the numeric data types that Postgres provides to us. In the last video, we were looking at the integer types, and in this video, we're going to start looking at the floating point type of numbers, or decimal numbers, which Postgres actually stores in 2 different categories. The first type is actually called floating point, and is considered to be inexact. We're going to see some examples of that as soon as we switch to the Postgres interface. But just a few pieces of information about those floating point type of numbers. They use a specification called IEEE 754, which we are not going to learn about in this course, but it suffices to say that it's a specification that tells a computer how it should store floating point numbers using binary, or zeros and ones. And in terms of Postgres, we actually have 2 types to represent these so-called inexact floating point numbers. We have the real data type, which can represent a number with a 0 dot followed by 37 zeros, up to a 1 followed by 37 zeros. So very, very small and very, very big numbers, but with only about 6 decimal digits of precision. So if you try to store something that has more than 6 things after the period, well, you might start to have some imprecisions right there. And we're going to see some examples of that. And if you need more precision or more range, Postgres provides the double precision, which allows us to store even tinier numbers and even bigger numbers. We're talking about a number with a 1 followed by up to 308 zeros after it, and with about 15 digits of precision. So these allow us to store numbers that will be inexact, but that will contain floating points and are usually used to represent scientific values. It's important to note that they can cause rounding errors. So we're not going to use these floating types of numbers whenever we want to store something with a decimal that needs to be precise. For example, if we intend for the price of an item to be of $19.99, we really want it to be $19.99. And if we use the real or double precision, well, that .99 at the end might be rounded off or might be changed to a .98 or .991 or something like that. And we really don't want that to happen. Same thing for interest rates and anything related to finance, where we know that every digit of precision matters. For those kinds of decimal numbers, Postgres will provide to us another type, which is actually called decimal. Postgres provides 2 names for that type, which are called numeric and decimal. But I just want you to know right away that these are just 2 names that mean exactly the same thing. So the idea here is to pick one and stick with it. In my case, I'm going to choose to stick with numeric. And if sometimes I happen to choose decimal, well, it's just important for you to know that they're both the same. And if you're designing one big schema in one shot, you're going to be sure that you're using the same one all the time. These decimal numbers are not only exact, but they can actually store huge numbers. You remember that that double precision type that we saw earlier allowed us to store a number with a 1 and about 300 digits after that 1. Well, with decimal numbers or numeric numbers, we can store numbers that have up to 100,000 digits in them. That's a lot. We can also optionally define a precision, which is the total number of digits that we would like to store for that particular column, as well as a scale, which will give us the total number of decimal digits that we can store, or digits after the decimal point. And these two are optional. So we can simply qualify a column as numeric, and it will allow us to store an arbitrary precision and an arbitrary scale with huge numbers up to 100,000 digits and more. You can imagine that having such a huge scale in the numbers that we can store comes at a cost. And indeed, choosing a numeric type comes with a cost, which is that it's very slow to calculate compared to integers or to those inexact floating point numbers. So we should only use them when appropriate. And the only way that you're going to know that is by practicing it and looking at more examples. And in this case, I've chosen to not actually create tables because I would like to show you another part of the Postgres syntax which relates to going from one type to another. So I've prepared an example here that will allow us to see the differences between numeric types and those real inexact types. And I'm going to do this by actually running some simple select statements. So I'm going to copy this first select statement here, which you notice is not selecting data from a column or from a table, but is simply selecting the result of adding two numbers together. I have judiciously chosen those numbers because they are going to create the kind of situation that I would like you to be aware of. So let's go ahead to our Postgres command line and paste that select statement, which is selecting 1.1 plus 1.2. And as you can expect, we get back the result 2.3, which is exactly what 1.1 plus 1.2 would be if you were to do it on a pen and paper or if you were to do it in your head. So far, so good. So it seems like Postgres understands numbers if we write them like this. Let's take a look at that second select statement that I prepared for us. Before actually pasting it in, let's first notice the difference between it and the first statement. Notice here that the 1.1 and 1.2 are between single quotes. Single quotes are used in Postgres to represent text, just like the employee names that we wrote in the past videos. So let's see what happens if I ask Postgres to do the addition operation on something that looks like a number, but is actually enclosed between strings. I'm going to paste that right in, and oops, there is a problem. Postgres could not apparently choose a best candidate operator. You might need to add explicit type casts. This is exactly what we're going to do. So Postgres here, what it's telling us basically is that we're trying to use the plus operator, which is an addition, between a string and a string. And even though those strings contain numbers, we've specifically single quoted them. So Postgres has actually no idea what to do with this. And there is a way that we can use a specific Postgres syntax in order to switch from one data type to another. And since we're right in the middle of learning about data types, I thought this was an appropriate time to show you this syntax. Notice our third select statement here, where we're using something very similar to the second select statement, but after the string. So we have a single quote, 1.1, and a closing quote, which we know represents a string, but then we're following that by colon, numeric. And we already know that numeric is one of the data types that Postgres provides to us. So what we're doing here is we're telling Postgres, really, take this string, which contains the value 1.1, and interpret it as a value of type numeric instead. And then we're using that plus operator again. And we're doing the same thing. We're taking another string, which contains 1.2, and we're telling Postgres to interpret that again as a numeric data type. What I would expect as a result of running this command would be exactly the same result as the first select statement, where we were using actual numbers, which, by the way, Postgres will automatically interpret as numeric. So let's go ahead and do that. Let's copy this command, which is using, again, this colon notation, which we call a typecast, and let's paste it right into our Postgres database. I'm going to clear the screen by using the combination of Control L on my keyboard, just so that I have a clean slate here, something that you should get familiar and used to doing in order to have less clutter on your screen. So I'm going to paste that command, and I'm going to get, again, the same result that I was expecting, which is that the value of the string 1.1 cast as a numeric plus the value of the string 1.2 cast as a numeric is giving me as a result 2.3. So where am I going with this? Well, so far, we've really only used numeric data types, which we already know are exact. So the reason why I chose these specific values, you're going to see in the next and last example in this video. So what am I doing here? Well, notice that in this last select example, I went back from using strings to using numbers. As I told you before, if I were to just type 1.1 like I'm doing in the first example, Postgres would automatically interpret that as being of type numeric. So what I'm doing in this last example here is I'm telling Postgres to take this 1.1 value, but actually interpret it as a value of type real, which is one of those two inexact type of decimal numbers that Postgres provides to us. And then to add it to the value 1.2, also interpreted as a real, which, as we know by now, is supposed to be an inexact type of value. And let's see what happens if I run this command in my Postgres database. If I run this command in my Postgres database, I get something that's a little bit weird and unexpected here. Instead of getting exactly the value 2.3, I'm getting the value 2.300002. It's not far from the correct value, but it's definitely not exact. And I'm using this specific example to show you how, in the realm of real and double precision values, which are the inexact decimal numbers provided by Postgres, there can sometimes be some errors in the way that those numbers are going to be represented. And while this might look insignificant, in the world of finance or in the world of e-commerce where you need some precision, it's going to be important to use the appropriate numeric type if you want to have an exact value in your calculations. If you were to represent the distance between two cities, for example, using meters, then it would be perfectly valid to use the real data type, right? If you have one digit of precision, you're basically at 1 centimeter or 10 centimeters of precision. And for the distance between two cities, that's perfectly valid. Actually, for most scientific calculations, we're going to be using real and double precision types of numbers. But wherever finance or prices or anything that really needs to be exact, or where we need to have really huge numbers of hundreds of thousands of digits, then we are going to use the numeric data type. And those are the two types of decimal numbers that Postgres provides to us. And actually, we've just gone through all the numeric data types that Postgres provides to us. After going through a few quizzes, we're going to go ahead and jump right into the text data types that are provided by Postgres. All right, so now you've become a pro at storing all sorts of numeric data types inside of Postgres. In this video, we're going to take a look at the text data types that Postgres provides to us. And even though, again, there are a lot of names in there, a lot of them are very equivalent. So at the end of this video, we should be able to figure out when to use which type of text data type. Postgres offers to us character varying, or varchar, character or char, and another type called text. So that seems to be like 5 types, but let's dive into them and see how they're more similar than different. All right, so let's take a look at the variable length data types. They are character varying or varchar. And one thing that you need to know is that they are exactly the same. So you should just pick one and stick with it. Now, these types will cause an error if you try to insert a value in a column that is longer than the limit n. So that n that we see here in parentheses in the definition of the type is actually the limit of the number of variable characters that you can store in that column. One thing that you need to know though is that that length is optional. And if you do not specify a length, then varchar will behave exactly the same as text. So there you have it. We have 3 different names here, so 3 different types of the 5 that we talked about, and they're pretty much exactly the same. Text will allow you to store text of unbounded length, and varchar will allow you to specify a limit on the length of the text that you want. And if you don't specify one, it'll act the same as text. In databases, it's very common to specify text or varchar without a limit. It just means that the database will not do any checks for us. And we'll see some examples of that after we looked at the fixed length text data types that Postgres provides to us. So here they are. They are character n or char n. And again, they are exactly the same. So you should just pick one and stick with it. They will also cause an error if you try to insert a value that is longer than that limit n that we have in the data type here. And they're actually rarely used because even though you might think that, well, there are a lot of things that are of fixed length, and you might have a false intuition that specifying a type of fixed length might actually be more efficient in terms of the database. Well, at least in terms of Postgres, it turns out that you don't gain any efficiency by choosing to use a fixed length character column. So an example of where you might want to use that is, let's say that your company sells products and has product codes to designate each product. Those product codes might be a specification of your company that you've had for years, and they're stored as, let's say, 6 or 8 characters. So then you would say, okay, I'm going to reserve a column of type char 8 or char 6, and I'm going to store all these product codes in there. And you're doing that thinking that you're going to save some space or some processing on the database because it doesn't have to figure out the length of the string or something. But again, it turns out that there is really not a lot of efficiency that is gained by doing that. And just as a historical counterexample, actually, it turns out that right about 2007, ISBN numbers, which are a standard for defining a number related to a book, went from 10 digits to 13 digits. So if you were previously storing those in a char 10 column, for example, well, now you need to change that column to a char 13. And as I've already mentioned, we're going to look later on in this lesson at a command that will allow us to change the data type of a column. But once you have a lot of data in a table, changing the data type of a column is something that takes time and could take your database down for a few minutes or even up to an hour or more. So it's something that you should really think about. And again, in most cases, you're going to be using variable length characters. So I've set up an example of a table that I'm creating here, which contains a lot of those types that we talked about. I'm going to copy this example and put it into our Postgres database. And we're going to run some inserts on it just to be able to see how it behaves exactly. But first, I would like us to take a look at this DDL statement here that I've crafted for us. So I've created a table of employees where we have an ID, which is a serial. We now know what that is. It's an integer type that is automatically managed by Postgres. And then there is a badge ID, which was pretty much an excuse for me to use that character type, which is again of fixed length. So if I try to insert something that's more than 6 characters for the badge ID, Postgres will throw me an error. And the weird thing is, if I have a badge ID which is less than 6 characters, well, Postgres is just going to pad it with white space so that it becomes 6 characters. So I really want to be sure that I'm storing only something that is exactly 6 characters in there and that it's never going to change, or otherwise I'm better off choosing a type varchar. So this is what I've done for the username. I've set up the username as a varchar of 30. Now, this is really important here This means that at the level of my database, I'm limiting the number of characters that a username that my employee can have to 30 characters. Why is it so important? If we are saying varchar 30 here, you can be certain that nobody in your whole company is ever going to be able to have a username of more than 30 characters. This is important because data goes through a lot of systems and a lot of phases, but usually the relational database is the last place where it's going to stay. This is why we refer to it as the source of truth, and this is why choosing the right data type is something that's really important when it comes to relational databases. So again, username is a varchar 30, which means that I will not be able to insert a username of more than 30 characters. If a username is less than 30 characters, then Postgres will store it very efficiently, only using about the number of characters that are necessary to store the username, plus a tiny bit of information to inform it of the length, since it's actually variable. So in all reality, you will almost never be using a full 30 characters or 30 bytes of information for storing this column. Finally, I have first name and last name, which I've set up as simple varchars. This is simply because as far as my business rules are concerned, I do not want to limit the number of characters that a first name and last name could have. I could go, for example, on Google and make a search, or go and open the Guinness Book of Records and search for what is the longest first name that a person ever had in existence, and then use that as my limit. But I've decided to use varchars without limit simply because I do not have a good reason to want to limit the length of the first names and last names of the employees of my company. So I did not have a good sensible value to put in there, so I chose to use varchar. Now, if you remember, we said earlier that varchar without a limit acts exactly the same as the text type. But if you look at the last column that I'm creating in this table, which is called biography, I'm choosing to use the type text here. It behaves 100% exactly the same as varchar, whether it's in terms of performance, of storage requirements, or whatever. So why did I choose one over the other? And why did I not just stick with varchar or stick with text? So in the case of first name and last name, my intent was to have a user be able to have a first name and last name that were of any length. Now, when you think of a first name and last name, even the biggest one that you've ever seen in your whole life, they're still usually something that will fit on a single line. And if you think of something like a biography or something like a blog post, you're thinking of a lot more text, right? So you're thinking maybe about even some paragraphs of text with multiple sentences in each them. You don't have to do this. No matter whether you choose varchar or text, they will behave the same way and allow you to insert the same kinds of data. So let's go ahead and create this table by copying this DDL command and pasting it in Postgres. And again, we're going to use the \d column followed by the name of the table. Again, using tab here in order to autocomplete the name of the table. And if I press enter, we're going to see that the table was created exactly as I intended. Notice that even though I mentioned that varchar and text behave exactly the same way, even in the description of the table, Postgres is making the difference and telling us that biography was set up as a text column and that first name and last name were set up as, well, it says character varying, but you already know that character varying or varchar is exactly the same way. So where I wrote the word varchar here, I could have written character space varying and then followed by a comma, and it would have had exactly the same effect. Here we see our username, which is a character varying 30, and we see our badge ID, which is of character 6, and our serial ID column. So in order to show you what happens when you insert data that does not fit, I'm simply going to craft a very simple insert statement. Remember that we're learning about inserting data in the next lesson of this course, but I'm simply going to craft a single simple insert statement where I'm not going to worry about any column at all. They're just going to have their default values, and I'm just going to insert a new employee simply with a badge ID that is longer than 6 characters. So this is going to be insert into employees. And then I'm going to list only the badge ID column because I don't want to insert values for any other column of that table for the moment. And then I'm going to say values, and then I'm going to insert a value by putting it between single quotes. Remember that double quotes are used for table and column identifiers, and single quotes are used for strings. So I'm going to input a badge ID here, which is of emp, let's say 4567, which is more than 6 characters. It's 7 characters. And so I'm going to copy this insert statement here, and I'm going to try to run it into Postgres. And immediately I'm going to get an error that says that the value is too long for type character 6. Again, in later lessons, we're going to take a look at how to change the data type of a column after it's been created. But remember, this is something that should be done sparingly. For now, the important is that we've created a table where we've used every character type that Postgres provides to us. In the next video, we're going to take a look at data types that we can use in order to store dates and times. All right, here we come to the last big series of data types that we're going to look at in terms of what Postgres offers to us. We've already seen how to store all sorts of numbers and all sorts of text data types. And when you look at a date and time, and you imagine it, let's say, written in its original format, like 2019-05-06, you could think that text type is sufficient to store a date and a time. You could just store it in a string and put the date and the time and be done with it. But there is a lot more to it than that. Postgres offers both date and time types that are completely different from strings, and it allows us to do a lot of calculations and a lot of operations on these dates and time types, so it understands what they are. So I would like to start by listing the list of those types. So we have a type called timestamp, and we have another one called timestamp with time zone. There's a very important distinction between them, and I'm going to show it to you with an example after we go through all the types. Then there is only a date type without a time associated to it, which is just called date. And there is actually just a type that allows us to store only a time. And then the important thing is to also know that there are some commands associated with those data types. So one of the most important topics when it comes to storing dates and times is actually time zones. So some of the first commands that we're going to look at are show time zone and set time zone. So let's take a look at those examples. I've set up a few commands for us to run in our database in order to get familiar with all those different types. After we look at those commands together, we're going to create a table, insert some values into it, see how it behaves, and become better at storing dates and times using the right type. All right, we've gone through a lot so far. Not only have we learned how to create proper relational schemas, we've also learned a lot of syntax and a lot of data types in order to bring those schemas to life inside the Postgres database system. Well, it happens sometimes that we make mistakes. It's not frequent, but sometimes it's necessary to modify a table structure after we've created it. And we're definitely going to look at some examples of that. Now, one thing to note is that if you've had a table that has been gathering data, let's say for up to a year, and then you realize that you need to make a change to that table, even though the commands are available and we're going to learn them, making a change to the structure of a table can take a long time because Postgres is actually to physically go through all the data set, all the data that is currently in that table, and modify it to match the new structure that you want. Sometimes, as an alternative, a database administrator will decide that it's actually better to create a new table offline while, let's say, the website that is backed by that database is still operating, migrate the data in the new format, and then sort of swap one table for the other. This is an advanced use case that is reserved for complex use cases and database administrator, and we're not going to really talk about that in this course, but I'm simply showing it to you in order to give you a sense of how modifying a table structure is really not something that you do on a daily basis and something that you should take seriously. That being said, here's the basic syntax. whereas creating a new table is done with the create table statement, and you can create multiple columns when you're creating your table. Modifying a table structure is done using the alter table statement, followed by the name of the table, and followed by an action that you want to do on that table. So I've prepared some examples for us to go through. All right, so the topic of this lesson was to study the DDL, or data definition language of Postgres. And so far, we've gone through pretty much most of the major commands that are used to define and modify the structures of our tables. In this video, I would like to just briefly go over all the other commands that compose the DDL syntax. So we are first going to list them, and then we're going to take a look at some examples together in our Postgres database. The first command is called drop, and it's a command that is used to remove a table from the system. You might remember when we were looking at the alter table syntax that we already used the word drop in order to remove a column from a table. Well, if we use the drop command by itself, we can actually remove a full table from the system. And again, this is not recoverable. It's completely destructive. Then we have the truncate command. The truncate command is used to remove all the data in a table. So you have a table of, let's say, of students, for example, contains 100 rows. You run the truncate command on it. The table is still going to be there and all its structure is going to be present, but all the data is going to be completely removed from the table. And all the name and the structure of the table will still be kept the same. And finally, there is another command that's really interesting. It's not really often used, but it can be useful in terms of documentation, and it's called the comment command. It's used to add a comment that is mostly for other programmers that are working with you on the same database. So I'm going to show you an example of that command, and I'm going to show you also how you can look at all the comments that have been created by you or your peers on tables that already exist in the system. So let's go ahead and look at some examples together. If you remember from past lessons, we've already had to insert data into our Postgres tables in order to see how it behaves when it comes to data types and data structures. So you're already a little bit familiar with the insert syntax. What you'll see in this video is that you can do a lot more than we originally saw in the previous lesson. So the basic syntax that we're going to be using is insert into table name, a list of columns, and then the word values, and then follow that by a list of values that are between parentheses. And optionally, we can add more of those values, which will each constitute a row in the database that we're adding to. We're going to see that there is a keyword called default that we can use whenever we want to insert the default value for a certain column. We're going to see that we can skip columns, which will automatically insert the default values for them. And we're going to do that right now using an example table that I've already set up for you. So I've set up a few insert commands that we're going to dissect and run together. But before actually looking at them, let's take a look at what we currently have in our database. What we have is a movies table. And if we describe the movies table, you will see that it contains 3 columns. An ID, which is a serial, which we know is an integer type that is automatically managed by a sequence. A name that is a varchar, or character varying, without any limit on its length. And a release date, which is of type date. And if we try to see what we have in this table right now by using table movies, you will see that there is no data in this table. This is exactly what we're going to do next, is we're going to start adding data into this table. So we have to insert new rows of data in the table, and we have to insert a name for a movie, which is a character type, and then we somehow have to insert a date for that movie. So let's see right away how we are going to do that. In this first variation, we're saying insert into movies, and then between parentheses, we're specifying the list of columns from the movies table that we are targeting. You notice here that we are skipping the ID column. We are not providing it. And so what this means is that Postgres, when inserting rows into this table, will use the default value for the ID column. And we already know that the default value for a serial column is basically the next value from the sequence. So in our case, we're simply inserting name and release date. And so once we finish listing the columns, we have the keyword values. And following that, we can put one or more rows of data that we want to insert. This is a good point where you can actually split your query into multiple lines in order to make it more legible. Notice that each row that we want to add starts with an opening parenthesis, and then the values for the columns that we are targeting, followed by a closing parenthesis and a comma if we want to add more rows. Now, in this case, the name column is a varchar. And so in order to add data into this column, here we are passing the value as a string. We are passing the name of the movie as a string, which is a perfect match for the varchar type. The release date, though, is actually of date type. And we already saw how the date type in Postgres is actually a lot more powerful than simply having a string which contains a date. But I would like you to pay attention to how we are inserting the data here. We are still choosing to insert the release date as a string that contains a date in the format of the year-month-day. Postgres understands this format. And since it already knows that the release date column is of type date, it will automatically cast this string that we're inputting into a date type. So the result of running this command will be that we will have 3 new movies in our database. Their IDs will be automatically generated because we are not targeting them. And the dates will be automatically cast from the strings that we are creating. In the last video, we saw that we can insert data into a Postgres table by providing a list of values that target different columns in the dataset. This is great. It allows us to bring some data from the real world and import it into a table and then be able to manipulate it, analyze it, and do various other things with it. There is another way, though, that we can insert data into a Postgres table. We can insert data by getting it from another table, something like a migration, completely changing the data from one form to another. And the cool thing about that is that you already know a good part of doing that, because you already know the SQL-DQL language, which allows you to select data from tables. And when you select data from tables, what you get back, if you do that, let's say in your Postgres command line, is, well, you get back a list of rows. And a list of rows is exactly what an insert statement is expecting. Even in the first form that we saw in the last video, what we were doing was insert into table name, a list of columns, and we were saying values, and what we were providing after that were a set of manually written rows. What we're doing in this form is that instead of manually creating the rows that we want to insert into the table, we're going to do that by selecting from other tables. So the best way to do that is to look at some examples that I've set up for you. Now, before looking at the examples and running them, let's take a look at the data set that I've prepared for you. So I've just logged into my Postgres database, and I'm going to issue the \dt command in order to list the tables that are in there. And we'll see that I have a table called post. I'm going to use the \d command, which will allow me to describe this post table and look at all the columns that are in there. So I have an ID column, which is a serial. I have a title column, which is of type text. And I have a category column, which is a varchar without a limit. Just as a reminder, you already know that varchar without a limit and text behave the same way. The only difference is that one has been chosen to be text because it was figured out that it would be longer than the other. So this is the post table. Let's take a look at the data in that table. I'll simply run select star from posts. And we will see that this table has already been set up with 6 posts that have an automatically generated incrementing ID, a title, and a category, which is in text and which actually gets repeated. So you'll notice that, for example, there are 3 posts that are in the travel category. So this is the data set that we have at our disposal. And what we would like to do with this data set is use it as a way to learn that second form of insert that we have. What I would like to do is I would like to create a new table that will be specific to categories and that will give a unique ID to each category so that I don't have to repeat its name. And then the way that I'm going to fill this category table is by actually selecting the categories that I currently have from the post table. In the last few videos, we've been practicing how to insert new data into Postgres tables. Now that we have some data into our tables, it's going to be important to know how to update it. So what we're going to look at in this video is the basic syntax to update already existing data in a Postgres table. And it goes update, followed by the name of the table, followed by the keyword set, and then the list of columns that we want to update, comma separated if there is more than one. So we say column 1 equals value 1, and so on and so on. And then there is a where and a condition. So since you're familiar with select statements that already use where in order to reduce the data set, you can already imagine what a where condition will do in an update statement. It will restrict the set of rows that are being targeted by that update. So a few things to note again is that we only list the columns that we want to be updated. If a table has 10 columns and we only want to update one, we just say set whatever that column is to the new value and we're done. Now, more importantly, if there is no where condition, this is going to ask just like a select. If I do select star from a table and I don't put a where, I'm going to get all the rows. If I do update from a table and I don't put a where, then all the rows are updated. You can imagine that this is not always what you want to do, so it might be really destructive. And there's no way to go back unless you have a backup. Now, the cool thing is that when you're updating the value of a column, you can use other columns during the update. And we're going to see quite a few examples of that in this video. I've set up a database for us that contains some data that we're going to be able to update. So far, you've learned how to insert and modify data in a Postgres table. Sometimes you need to get rid of old data. And in this video, we're going to learn the syntax for deleting data in Postgres. The basic syntax is delete from, followed by the table name, and then where a certain condition that must be met. Now, again, just like for the update, if you do not specify a where condition in your delete, then all rows are deleted. You can imagine that this is very destructive. Also note that if you were to not provide a where, there are some differences with that truncate table statement that we saw from the DDL section. If you remember, using truncate table, we had a way to be able to reset the ID sequence that we had. But if we're just using delete from table without putting any condition, we're just deleting all the rows in the data set. So there are some differences between both. Let's take a look at some examples of deleting data. To do that, I've prepared a data set for us that we're first going to start by exploring. So far, you've learned how to insert and modify data in a Postgres table. Sometimes you need to get rid of old data. And in this video, we're going to learn the syntax for deleting data in Postgres. The basic syntax is delete from, followed by the table name, and then where a certain condition that must be met. Now, again, just like for the update, if you do not specify a where condition in your delete, then all rows are deleted. You can imagine that this is very destructive. Also note that if you were to not provide a where, there are some differences with that truncate table statement that we saw from the DDL section. If you remember, using truncate table, we had a way to be able to reset the ID sequence that we had. But if we're just using delete from table without putting any condition, we're just deleting all the rows in the data set. So there are some differences between both. Let's take a look at some examples of deleting data. To do that, I've prepared a data set for us that we're first going to start by exploring. Now, so far, even if you don't know it, you've actually been running every command in your Postgres command line as part of a transaction. There is no other way. So we'll see how that happens in a few moments. For now, just know that you can start a manual transaction using the command begin or start transaction. These commands have exactly the same result. They actually manually start a Postgres transaction. After running these commands in your Postgres command line, you can run any SQL you want. You can delete tables, you can delete rows in tables, you can do anything you want. And as long as you don't run another statement that says end or commit, which are both equivalent, whatever operation you did are not going to be persisted in the database. More importantly, if you run the rollback command instead, then you're also putting an end to that transaction that you started. But what you're saying is that whatever you did during the period where you started the transaction and your time where you did rollback is actually not going to happen. You are basically allowing yourself to change your mind. Now, as I said before, you've already been using transactions without realizing. The reason for that is that t-sql, which is the command line that we've been using to interact with Postgres, has a feature called auto-commit that is on by default. And so every command that you have been running in your Postgres command line has actually been committed automatically. So the first thing that I would like to show you is how to turn off this behavior and what impact it has. And after we see that and our auto-commit is finally off, we are going to start looking at doing some manual transactions and seeing how they will affect the data that we have in our database. So let's first start by going to our Postgres command line and setting auto-commit to off. But before doing that, we should explore what we currently have in our database.